Hello friends, welcome to Joy of Life. So today we're going to look at another medium level problem from Leetcode. The problem number is 215. Kth largest element in an array. So given an integer array nums and an integer k, return the kth largest element in the array. Note that it is the kth largest element in the sorted order, not kth distinct element. Okay. So we have some examples over here. So let's look at them and understand them in a little more details. So here we have an array, right, which have elements like 3, 2, 1, 5, 6, 4. And we have the second highest element over here, right? We need to find the second highest element. So if you look at this array, the first highest is 6, the highest. And then we have the second highest, which is a 5. So we need to return this 5. So the output is 5. Again, this is the fourth largest element in this array that we need to find. So this is the first highest, this is the second highest, this is the third highest, this is the fourth highest, right? So we need to return this 4 over here as the answer. So this is a very common interview question. Do give it a try. Do try to solve it yourself. Just try to think and come up with the logic, and then you can check out my solution in the board. So let's move over to the board and check out the solution. So I've taken the same example from Leetcode. We have the array 3, 2, 3, 1, 2, 4, 5, 5, 6, and k is equals to 4, right? So here we have some duplication of elements. You can see that 3 is repeated, 2 is repeated, 5 is repeated, things like that, right? And we need to come up with the fourth highest element over here, right? So whenever you get a problem wherein you have to find the second, third, fourth, max or min in a given array, tree, or any data structure, the solution is that we have to maintain a data structure where we can keep the data sorted and we can move the data in and out in a very efficient manner, right? So there is a data structure which can help us to get this sorted out is called heap. So let's talk about a heap over here. So let's talk about a, let's say, max heap. So what happens in a max heap? In a max heap, we have the root element, which is the maximum of all the inserted element. Then the child is the next highest element, either of the child, and it follows. Then their child has the next highest element, and so on. So if we take this example that we have over here and try to put them in a heap, what will happen? So I will first put a 3. So nothing is there. 3 is the root of the heap, right? Then I put a 2. So 2 will come and sit over here, right? So as soon as I insert this 2, what happens is the heap verifies that is it breaking the contract of the heap? So it sees that no, it's not breaking the contract. Then I get a 3 and I put the 3 on the left side. So keep in mind, in a heap we fill from top to bottom, left to right, right? So again, this is not violating. So 3 is the highest sitting over here. Then I get a 1. So 1 goes to the left of 2. So 1 comes over here. The moment 1 comes, we see that is it still maintaining? I see, yeah, it's fine. It's not violating. All the relation, like 3 is greater than 2, 3 is greater than equal to 2, 2 is greater than equal to 1. So it's all fine as of now. Then the next element that I get is a 2. And I put the 2 and I continue to see that it's fine. It's not violating any of the properties of the heap, right? And then what happens is I get a 4. So I put the 4 over here. So the moment I put the 4, what happens is the heap checks that is it violating. It says that yeah, it is violating the constraint. So what happens is it does a swap with the parent node. Something like this happens. So these two nodes over here got swapped. These 3 and 4, right? So it checks does 4's parent does it still violating? So it says yeah, it is still violating. So what it does, it again does a swap with its parent. So this 3 comes over here and this 4 is promoted to the root of this heap, right? So now this heap is fixed. It does not contain any problem. Then again, what happens? We get a 5. So this 5 is inserted over here and it checks does 5 violating. So we see that the parent of 5 is still violating the condition. So we take this guy out and we take this 3 over here. We put the 3 and we put the 5 back as the parent of this nodes, right? So this is what happens. And then it checks again and it finds that 5 is still violating. So what it does is it takes the 5 and it does a swap with its parent. So 4 again comes back over here and 5 is again promoted to the top of the heap, right? So this is what happens in the heap. And now we get the next 5, right? So we put the next 5 over here and we continue to do the same check. So first I see that yeah, it's the 1 is violating, 1 is smaller than me. I get the 1 below and I put the 5 over here. Again I see that the 2 is still I again see that the 2 is still violating. So I take the 2 out and take this 5 and do a swap with its parent. So this activity continues over here, right? So this is what ends up after the swap, right? This 5 and 5 is fine. Then I get a 6 again over here. So by the rule, we put the 6 here and we see that, yeah, 6 is again violating. 2 cannot afford to be 6 parent. So we take the 2 out, take the 6 and put it in its place. And then take the 2 over here. And then take the 6 and do a swap with this guy over here. And put the 6 over here. We still see that the heap is not fixed. We take the 6 again, does a swap with its parent over here. So the 5 comes and sit over here and the 6 goes over here, right? So all the items has been inserted into the heap and the heap looks good to me now. It's a max heap. It's holding its condition of a max heap. Now we need the fourth highest element, right? Now if I start popping out from the heap, what will happen? 6 will be popped out first, right? So I pop out 6, and what happened when the 6 is removed? 5 and 4 compete to become the parent, right? So 5 wins. 5 is a clear winner over here. So 5 gets promoted to the top. Now this is a vacant place. So 2 and 5 competes. Who can go here? Of course 5 is greater. So 5 will have the priority. So 5 will come and sit over here, right? Again 1 and 2 will fight to take the place of the parent. So what happens over here? 2 is a clear winner because 2 is having a higher value. So 2 will come and sit over here. So 6 is the highest element we know. Then we pop out again. So next time when we pop, we get the 5. Again the 5 and 4 competes, and what happens is this 5 is promoted as the root of the heap because 5 is greater than 4. So there is a vacancy over here. These two fights over here. So let's say either of the 2 wins based on your logic. So let's take this 2 and place it over here. And what happens is we can remove this line and put 1 back. So after 2 times pop up, the heap looks something like this, and then we pop out again. So we get another 5. 2 and 4 competes this time. 4 is a winner because of its value. So 4 comes to the top, and then both of the 3 competes. And this 3 over here is, let's say, promoted to the top, and we pop out again. So now you see we have popped thrice. Now the 4th time we pop out of this heap, what we get is the 4th highest element over here, right? And this is our solution, exact solution going to be. We have understood the solution using a max heap, which is a very nice kind of solution which will have an order of n because we are storing everything. Now let's think about it in a reverse manner, right? Let's talk about a main heap over here. So in a main heap, what happens is the opposite, right? In a main heap, the concept is the same, just that the minimum element remains on the top, right? Nothing else changes, right? So we put the 3 over here. We get 1 element, so 3 stays where it is. Now I get a 2. So when I get a 2, what I do is I check, is 2 smaller than 3? Yeah, it is smaller than 3. So what I do is I get the 3 out and take the 2 to the top, right? And then what happens? I get another 3. So I put that 3 over here and everything looks fine. The minimum element is the root of the heap, right? And then what happens? I get a 1. So with this 1, what happens is I check that, is my parent greater than me? Yes, it is greater than me. So what I should do? I should immediately do a swap. So here I am. I put the 1 back over here and the 3 goes below. And again I check, is 2 greater than me? Yes, it is. So immediately I go for a swap with my root, and 1 is promoted as the root of the 3 over here, heap over here. So the heap looks like this. And what we do over here is we keep a track that is the size of my heap greater than k. So I see the size of my heap is not greater than k. So I'm fine. So I'm done with the first 4 elements. Then I get a 2. And according to the law of this heap, I put the 2 over here. Anything violating? Nothing is violating. Everything looks fine to me. But the only thing that's violating at the moment is that k is greater than 4. We have 5 nodes over here. So we pop and we discard the root of the heap. So this has been discarded. So let's put it as discarded. Now 2 and 3 over here fights to become the root of the heap. So clearly 2 is smaller. So 2 will win in this case and 2 will be promoted as the root of the heap. And then again 2 and 3 will compete, and these 2 will, this time this 2 will win it and it will go over here. So the heap will look like this, right? So let's maintain the position where we are also. So we are done with 5th element, so we come over here. So we get a 4 and we insert the 4 over here. As we insert the 4 over here, we see that again we have 5 elements. So we do a discard of the root of the heap. And again 2 and 3 competes. This time also 2 wins. So 2 goes to the top. 4 and 3 competes. So 3 comes over here. So we have 4 elements and again we move on. We come over here. So we get a 5. And also do keep in mind just a point that I missed, that this will come to the left side. We have to get this balanced. So we come to the next node, which is a 5, and what we do is we insert the 5. Again we take the root of the tree and we discard it. And so again these 2 3 competes, and let's say this 3 comes over here, and then 4 and 5 competes. So 4 comes over here and 5 goes to the left edge. So our heap becomes something like this. Then we get another 5 over here. Then our pointer moves on to the next element, which is also a 5. So what we do is we put the 5 over here, and again since it is exceeding the size, so we take and discard this node out, and we check who can become the parent. So here 3 can become the parent. This 5 over here can come to this edge. So our heap looks something like this. Then we move on the pointer. What we get is a 6 now. So we put the 6 over here, and again we take and discard the root of the heap, and 4 and 5 competes. 4 is a clear winner, so 4 goes to the top. 5 and 6 compete. 5 is a clear winner, so 5 goes over here, and 6 come to this edge. So this is how my heap is after I have inserted all the elements and have maintained the size at 4. So whenever it exceeded 4, I just popped out the root element. So grammatically you can see that if I pop one element out from the heap, my next element is nothing but my answer over here, right? Why this will happen basically is that we are having the heavier elements at the bottom and we are maintaining the size. So whenever you need to find the max, it is recommended that you use a mean heap, right? And whenever you need to find a min, you are supposed to use a max heap. So that will give you an optimum result, right? So over here, if you see that we have not exceeded the amount of k storage, right? So our space complexity for this problem is order of k, right? So this is the solution all about. You can try out the previous solution as well using a max heap, but mean heap will give you the most optimal solution in this case. So let's move over to Leetcode and check out the solution. So mostly in Java, what we do for a mean heap is we use a priority queue. You can have a custom implementation also, that's also completely fine, but you can use a priority queue. So let's use a priority queue over here. Let's name it priority queue, and let's build a priority queue over here. And by default, the priority queue works as a mean heap. So if you want to override and use a max heap, you can pass a couple of parameters over here to modify it, right? So what we are going to do is we are going to iterate over nums, and we are going to push into the heap. So pq.add we are going to do of n, and at any point if you see that pq.size is greater than k, the way we have talked, so we are just going to remove elements. This is as good as discarding because we are not taking the elements anywhere. So we are just doing a discard over here. And at the end, if you remember, what happened was we had the element on the top over here, right? This row. So we have to just basically do a pq.pull, and this would give me the element that we are looking for, right? So let's run this code and check. So yeah, it's been accepted. Let's submit and check for a wider range of test cases. So we have a 8 millisecond performance, 22.79%, though I feel there is some problem with Leetcode over here. So just to show you again that I'll do a submit and you will get a better or a worse number than this for the same solution. So you can see that if I continue to submit, you will get different results at different point of time. So don't go by it. So basically it was all flawed up things. So previously when I was trying over here, I got a 4 millisecond for exactly the same solution when I was preparing the video. So I'm not sure how accurate those numbers are, or maybe it varies with the subscription or not. So that is something that Leetcode should do and take care of it. So you can see that now it's giving a 4 millisecond. Previously it gave a 10 millisecond, a 7, like a dramatic change in performance. So I would request the folks in Leetcode to check this. There is something very wrong with this. So don't go by that Leetcode number, even I don't care about it. The main intention over here is the solution. So what we are doing is we are iterating over the entire array list, right? As we have seen in the code over here as well, right? So your runtime would be order of n because you are iterating over everything, right? Where n is nothing but your length of the array that's passed to you and your space. So at any given point of time, using this approach, what will happen is we are not going to have more than k elements stored in our uh, heap, right? So it will be order of k. But if you are going with the earlier approach that I have shown you with the max heap, then it would be order of n. That's not an optimal space solution, but yeah, the runtime would be pretty much the same. So yeah, that's all from this video. Do let me know what you think about this video. Do give it a like if you think this video was helpful. Do share and do share with your friends and try to promote the channel if you think the solution is helpful and could help others as well. So yeah, if you're a first time viewer, definitely subscribe. Here I mostly post programming solutions and I have plans to expand it, though I keep on posting some unboxing things as well, whatever I order and things like that. But yeah, that's mostly for relaxation time, but it is mostly dedicated to the programming part. So do share and subscribe with your friends. I have created many playlists also based on programming things, so do check them out. Do share with your friends. Yeah, that's all from this video. And once again, the situation outside is not at all great in India. So do stay at home, be safe, keep your family safe, don't go out, don't come in contact with the virus, try to break the chain and help everybody out there. So yeah, that's all from this video. See you soon. Bye bye and take care.